Hi. We started another new section this week, chapter 11, which it probably seems kind of strange because we were doing all this stuff with distributions and joint distributions, and now chapter 11 concentrates on something that we call moment generating functions. And I usually just shorthand MGF. And the reason why we do moment generating functions, well, first, it can give us moments of a random variable, but it can also, I think it's much more important for other things. Namely, it gives us a nice way of learning how to sum independent random variables. Otherwise, this can be very, very difficult to add random variables like x plus y or any combination. This is a very, very, very tough problem in probability, so that's one reason why we use moment generating functions, because they're very helpful for this, to find out the distribution of sums. Alone, I mean, it's nice to see what moments, how to determine moments. There's a very nice way to do that, but in general, this is the more important reason for doing them. So we have a comic, and so I thought I would just introduce them in the first video and then do some examples in the next one. So when we talk about moments of a random variable, that's just the expected value of x raised to the kth power, where k is the moment I'm trying to determine. So the first moment is just the expected value of x to the 1, which you already know is the definition of the mean mu. The second moment is expected value of x squared. That's why I say second moment. This isn't the variance, but we know that the variance is the combination of, here's the second moment minus the first moment squared. The kth moment is just expected value of x to the k. And there's other things we can find with moments, like skewness. Skewness is like the amount of the distribution in a tail. Like we'd say this guy is right skewed because it has a long right tail. So expected moments of higher powers like x cubed, x to the fourth. You can find things doing combinations like skewness, kurtosis. Kurtosis is just the peakedness, like how peaked, flat across or tight a distribution is. A nice property of moment generating functions is we can distinguish random variables by their moment generating functions, because no two different random variables have the same MGF. So if you can identify a random variable's moment generating function, then you know what distribution it has. So this is a very nice property. What is the definition? So we should get to the definition now. Right now, I'm just saying is moment generating functions are expected value of x to the k. So how do we find, or what's the definition of a moment generating function? Here it is. The moment generating function of random variable x in terms of t is expected value of e to the tx. And we know how to find expected value of a function of a random variable. We just use law of unconscious statistician. So down here, that's all I'm doing. This is expected value of e to the tx, so I put e to the tx times p of x times x, so it's just e to the tx times p of x. This is just that law, right? Remember, expected value of something like x squared was just the sum of f of x times x squared. So I'm just using this as my inner function right there to put p of x times expected value 2x. So if x is continuous, same deal. And notice the only difference, if it's discrete, we have the nice sum, and continuous, we have a nice integral. And sometimes, of course, this integration might not exist, so you might not have a moment generating function for some random variables. Same way with the discrete. So let's go down and notice now why the moment generating function finds means and variances for us. This is, I think, really cool. So I'm going to assume x is a continuous random variable. So the definition of the moment generating function is just this. So all I'm doing right now is the definition. And now I'm going to write out the power series. Oh yeah, these things come back to you from calculus. The power series of e to the tx is just this. So I'm just substituting this in for e to the tx. Oh, I hope this doesn't stop or I'll be sad. Remember this happened to us before. Let me see, maybe I can switch to another program and come back. No. Well, you probably can't see this, but so all I've done right here is definition, and then I'm going to go ahead, you can see the next line, so let's just go there. If I multiply 1 times f of x, I get this. If I multiply t of x times f of x, I get this. So I'm just going to expand and then separate them into separate integrals. You can see what I'm doing there, right? This is going to be an infinite sum of these integrals. Well, 1 times f of x dx over this interval is just 1, because this is the definition of a valid probability density function. This right here, x times f of x, is just expected value of x. X squared times f of x is expected value of x squared. X cubed would be expected value of x cubed. Down here, this is expected value of x to the k. So notice nicely, the moment generating function can be written this way as an infinite sum. We're going to use this then to find means, variances, etc. So I think I'm going to stop and see if I can start a new annotator video. I don't want to lose what I already have, so